The unusual Comet 3I Atlas, which arrived in the solar system from interstellar space, unexpectedly shifted to a bright green hue during a rare observing opportunity, a total lunar eclipse. On September 7th, astrophotographers Michael Yeager and Gerald Riemann in Namibia captured this colour when the moon's light nearly vanished, opening access to faint objects. Scientists are discussing the causes. The classic source of a green coma is diatomic carbon, the C2 dicarbon molecule. But spectra of 3I Atlas have not yet confirmed it. An alternative is emission from cyanides, whose presence in the coma has already been reported. It's possible we're witnessing rare chemistry that has yet to be described. This unexpected green note is another stroke in the Wanderer's portrait. When a guest from the interstellar depths flies into our solar system, it's always an event. The Comet 3I Atlas is only the third such wanderer ever recorded by humanity. And as befits a rare guest, it isn't behaving quite as usual. But first things first. Over the past week, 4 powerful telescopes, Hubble TSS Spherics and the James Webb Space Telescope, confirm that this comet isn't following the usual script, and now the unexpected green tint of the coma has added further mystery. That draws even more public attention. Its coma, the cloud of gas and dust surrounding the nucleus, has turned out to be unusually rich in carbon dioxide. Water here is roughly 8 times less abundant than is typical for comets. At the same time, the green tint is not yet explained by dicarbon. The spectra haven't revealed it. A possible contribution from cyanides is under discussion. Various explanations are possible. The nucleus may have formed where the carbon ice line lay closer in, on the cold outskirts of its native protoplanetary system. Or the ice survived for millions of years under intense radiation, and the balance of substances changed. There is also a third version. The internal structure of the nucleus may restrain the sublimation of water, while freely releasing carbon dioxide. At the same time, no bright tails or characteristic gas streams, the so-called jets, have yet been observed. It's as if the comet is gathering strength, preparing for a big performance, or contact. On October 29th of this year, 3I Atlas will make its closest approach to the Sun. But for observers on Earth, this moment will be hidden in the Sun's bright glare. Perhaps the real show will begin later, when the comet starts to move away and passes closer to Earth. In March, its path will carry it past Jupiter. There is a chance that the Juno probe will catch it in its field of view. And by all indications, 3I Atlas is ready to surprise us more than once. So far, we know the following. It is travelling at about 58 kilometers per second, which makes it the fastest interstellar courier ever discovered. Its diameter is estimated at roughly 11.2 kilometers, which also makes it the largest known guest of the solar system. Unusual scale goes hand in hand with unusual behaviour. Trajectory analysis has shown that 3I Atlas likely came from the thick disk of the Milky Way, where old stars reside. By one estimate, its age is between 7.6 and 14 billion years, potentially older than the solar system itself. Its visible cloud of gas and dust reaches up to 26,400 kilometers in diameter. Its dust tail is at least 25,000 kilometers long. Its unusually large size, very long tail, ability to release more carbon dioxide than water and nickel without iron, as well as a route past 3 planets of the solar system, have prompted a new study suggesting that this guest is not a comet at all but an interplanetary ship. The word interstellar itself sounds like a challenge. We're used to thinking of comets and asteroids as ours, solar. And here is something alien, flown in from the depths of space. It's no surprise that along with the news about 3I Atlas, dozens of headlines flared across the media space. Alien ship, probe of another civilization, threat to Earth? Will we all die? Yes, sooner or later, but that's hardly what this story is about. It's no secret that the story of this object has spawned a flurry of hypotheses, including the idea of unprincipled aliens. Why does this happen? The fact is, 3I Atlas seemed unusual from the very first detection. It moved along a hyperbolic trajectory. Its path was too accelerated to remain in the solar system. That already meant one thing: it arrived from interstellar space and will never return. Such guests are extremely rare, and every time humanity encounters something new and utterly fantastic, legends and myths inevitably arise, be it the Loch Ness Monster, the Yeti, or an honest politician. In the case of interstellar objects, the logic is simple. If they are alien, then perhaps alien tentacles made them. For example, Oumuamua surprised astronomers by accelerating as if pushed by sunlight pressure, not just gravity. A similar impression arises with the third interstellar wanderer. The object seemed so strange that one of the once most famous astrophysicists, Avi Loeb, retrained as a ufologist and directly suggested, "We are seeing not a rock, but a fragment of an artificial sail." The media immediately seized on the alien ship and marketers on selling foil. That's how people are built. They tend to look for intention where there is a mystery. If an object flew in from the depths of space, then someone sent it. If it behaves unusually, then it is hiding something, and if it passes by Earth, then its target is Earthlings. Mysterious? Yes, it's hard to argue. So what arguments do supporters of the alien hypothesis put forward? First, they point to the unusual trajectories of interstellar objects themselves. To break away from its star, an object must either initially have colossal speed or be thrown out by some powerful gravitational process. That's a rare event and therefore suspicious. Second, shape and behavior. To many astronomers, 3I Atlas seemed elongated and flat, while showing puzzling acceleration. Third, the cultural factor. We are raised on stories about visitors from space. We watch science fiction films, read novels, and perceive any astronomical news through the prism of these plots. Therefore, the very idea of an alien probe is seen not as a crazy fantasy, but as an option worthy of discussion, and that shapes public expectations. Fourth, the enigmatic flickering. Some astronomers and photographers note strange flashes of light in images of the Comet 3I Atlas. At present, there is no scientific evidence that the object emits lights reminiscent of a UFO. Most likely, these are optical interference in the photographs or reflections of light from the comet's icy surface. Nevertheless, the comet's unusual manifestations have aroused lively interest and speculation in the scientific community. For some observers, these flashes are associated with scenes from the films Contact and Arrival. In Contact, scientists record mysterious signals from space, possibly messages from extraterrestrial civilizations, while in Arrival, strange objects in the sky raise questions about the intentions of aliens and about how little humanity knows of the universe's scale. In the end, we have two versions of what's happening. One is strictly scientific and rational, explaining everything by reflections and an icy surface. The other is almost fantastical, giving rise to thoughts of extraterrestrial signals and space mysteries that humanity is not yet able to unravel. It is this duality that turns observation of 3I Atlas into a true cosmic detective story. And to finally sort it out, astronomers have proposed an unconventional method of study to redirect one or more existing interplanetary spacecraft to it. However, neither NASA nor other space agencies have yet responded to this initiative, and some opportunities have already been missed. The situation looks discouraging in the eyes of the scientific community and pushes researchers to look for new solutions. For example, a new idea was born in an SWRI project. Its participants posed a simple but ambitious question. Is it possible to catch up with an interstellar comet? Such objects fly by very quickly, and there is usually no time to prepare. For this, a probe is needed, but not an ordinary one. It must reach huge speeds and be launched within a few years of the target's discovery. We would have to use gravity assists, powerful rockets, and even electric propulsion, all to catch up with 3I Atlas or its future siblings. The problem is that technically this is extremely difficult. at least for now. Interstellar objects move at speeds of tens of kilometers per second. That means a chasing mission would have to surpass everything humanity has launched before. Is it possible? Certainly, once technology advances a bit further. In the meantime, 3i Atlas reminds us, the solar system is not isolated. The solar system is not isolated. It is a crossroads where, from time to time, a guest appears with no habits and no schedule. 3i Atlas has already passed its closest point to the sun, hidden in the bright glare, and is now slowly emerging from that light. Right now, the silence around it speaks louder than any headlines. If anything in its behavior changes, we'll notice. First comes the breathing. That's how astronomers sometimes refer to a comet's weather. How the coma changes, whether the tail stretches out, whether jets of gas appear like thin fountains. With 3i Atlas, everything remains unusually calm for now, and that's no reason for disappointment. On the contrary, the quiet is a clue that its internal processes run differently than in familiar comets. Imagine a frozen window in winter, patterns on the outside, while warmth from the room spreads unevenly. In some places the ice thaws quickly, elsewhere it lingers. Something similar may be happening in the nucleus of 3i Atlas. Porous upper layers give carbon dioxide a short path to the surface, while water gets trapped deeper down, where it's harder to break through. When an object moves away from the sun, its temperature doesn't drop immediately. Rock and ice hold heat like a kettle taken off the stove. It no longer boils, but it stays hot for a long time. That's why a comet's tail is sometimes more noticeable after perihelion. If 3i Atlas still doesn't grow a tail now, it won't mean nothing happened, but rather something we didn't expect happened, which is even more interesting. While we watch the coma, it helps to keep simple facts in mind. Its speed is about 58 kilometers per second, fast for an interstellar wanderer and a serious challenge for our missions. A fast guest means a short observing window and rapid changes in geometry, when it's too late to launch but impossible to turn off curiosity. It teaches us to value every night and every spectrum. The nucleus is estimated at roughly 11 kilometers across, a lot by the standards of rare visitors from beyond. Large doesn't always mean bright. If the surface is covered with dust and a crust that poorly conducts heat, activity remains quiet and even. Instead of spectacular jets, we see soft, steady sublimation. Beautiful in its own way, and very informative. The coma of 3i Atlas is rich in carbon dioxide, while there is less water than expected for a typical comet. This can be explained in three simple ways. A birthplace in a carbon cold zone, a long radiation history that changed the balance of ices, or a porous nucleus structure that releases CO2 more readily than H2O. Each of these versions is being tested by observations, calmly and step by step. Discussions sometimes bring up a detail about nickel without iron. It sounds mysterious and begs for splashy headlines, but essentially it's an oddity in the dust and gas that needs rechecking and careful explanation. Such details create duality, natural and fantastical versions standing side by side. The important thing is that both start from the same data, and it's the data that settle the debate. The trajectory of 3i Atlas is hyperbolic. That's a simple truth without embellishment. The sun's gravity isn't enough to hold the guest. It came from interstellar space and will leave again. What will remain to us are traces in spectra, images, and tables. Sometimes that's enough to understand far more years later than it seemed at the time of the flyby. In moments like this, you want to get closer. Any camera on an interplanetary spacecraft, any lucky flyby is a chance to glimpse the past. But the dream runs up against math. To catch up, you need to accelerate harder than we're used to, and in time. The windows, when we could launch right now, often open while we're still arguing about propulsion schemes. The good news is that closer isn't only kilometers. Closer also means listening properly. Spectra tell us which gases are escaping and how their fractions change with distance from the sun. Photometry hints at how steadily the nucleus rotates, and radio observations help estimate dust grain size and coma density. There's a human side to this as well. We grew up on films and books where the sky speaks to us directly, and on seeing a strange object we instinctively switch to the language of science fiction. There's nothing wrong with that. Scientific language is simply slower, like calm speech before sleep. First facts, then hypotheses, and only then big conclusions. If we see 3i Atlas not as a threat but as a teacher, it gets easier. It shows how little we know about materials born outside our system, and pushes us to refine our models of sublimation and heat transfer. We teach it the patience of instruments, and it teaches us to hear the quiet. It's an honest exchange. Right now, the best thing we can do is watch longer and more carefully. Check reports of flashes, look for patterns, compare night to night, and avoid chasing sensation. Small bricks of certainty stack into a pattern that's hard to see in a rush. If the pattern emerges, we won't miss it. People sometimes ask, what if it's a ship? The correct answer is dull but sound. First we test the simple explanations, then we tackle the complex ones. A flat shape can turn out to be a play of light and viewing angles. A dry coma, a feature of origin and irradiation, flashes, optics, and reflections. If these versions don't survive testing, we'll honestly move on to the next ones. Even if everything's explained without science fiction, the wonder doesn't go anywhere. The wonder is the fact itself. A piece of the past flew to us from another part of the galaxy, and we can hear its whisper. The wonder is the patience of instruments and people who turn weak signals into meaning. There's a quiet but powerful beauty in that. In the coming months, 3i Atlas will move farther from the Sun and pass parts of its trajectory that are convenient for different observing bands. Some will get clear nights and wide fields, others dry tables of numbers, and someone may be lucky enough to catch a glance from Juno. From this motley material, the answer we need will take shape. Let it be not loud, but simple. For example, inside this nucleus live ices that have never been comfortable near light in our neighbourhood. Or, this body was born where CO2 froze before water, and now that's visible in every trickle of gas. Or perhaps we've just underestimated, quite and overestimated familiar scenarios. If the answer's unexpected, we'll handle it. Science exists to be surprised properly. First check, then understand, and only then name. 3i Atlas doesn't owe us anything, but it has already given us a gift. A reminder that the world is bigger than our habits. What remains for us is the main thing: to watch, listen, and record facts that don't shout. When they link into a chain, we'll see more about 3i Atlas and about ourselves. We're used to thinking that a comet is first and foremost water. Ice warms, evaporates, drags dust along, and the sky sketches a familiar tale. With 3i Atlas, everything is different. Its breath contains more carbon dioxide and noticeably less water than we usually see. This isn't a random quirk, but a trace that leads to its birthplace and a long history. Imagine a large refrigerator in which different gases freeze on different shelves. Closer to the door, where it's a bit warmer, water doesn't linger, while carbon dioxide can still remain ice. If 3i Atlas accreted in such a zone, then under our sun's rays it's not water that will speak first, but CO2. It's as if we're listening to that refrigerator billions of years later. There's another simple scenario. A long life between stars means years under a gentle but constant shower of high-energy particles. Such a shower alters the skin of the nucleus. The upper layers grow denser, and the chemistry becomes poorer in water. Carbon dioxide passes through more easily, water with greater difficulty, and in the spectrum this shows up as inverted familiar ratios. The nucleus's porosity adds another detail. An extended network of micropores gives CO2 short tunnels to the surface, while stickier water gets delayed, refreezes and tries again. So 3i Atlas can remain outwardly calm, without showy jets, yet continuously and evenly release carbon dioxide. A quiet process isn't a weak one, just a careful one. How do instruments learn this? They split the light into colours and look for the fine signatures of molecules. For carbon dioxide and water, those signatures lie in the infrared, and spectrographs see them as neat lines and bands. The taller the band, the more molecules escaped, the louder the coma breathes. We are quite literally reading the gas aloud. Over time we can track how the CO2/H2O ratio changes with distance from the Sun. For familiar comets, the curve looks one way. For 3I Atlas, it will likely be another. If the water fraction barely grows even after perihelion, that's another argument for a carbon zone of birth or a deep desiccated crust. Each night adds a new point to that curve. Talks also mention nickel without iron. The words sound intriguing, but accuracy matters more than intrigue here. Sometimes that's how small impurities in dust appear, or processing errors. Sometimes it's a real signal that needs repeats and comparison with standards. Until then, it's just a question with a bookmark in the margin. With dust, everything is subtler than it seems. Particle sizes affect the tail's colour and the way light scatters in different directions. If the dust is coarser, the coma can appear warmer in the infrared and heavier in images. If finer, the opposite. Hence the effect. The eye expects a bright brush stroke in the sky, while instruments show a soft, broad cloud without sharp patterns. Another simple check is how quickly the coma dims when the Sun drops beyond the curve of the orbit. If gas is coming from depth, the decline will be slow, as if someone hasn't quite turned off the tap. If everything depends on a thin surface layer, the light goes away and activity quickly weakens. From the shape of that curve, it's easy to tell a shallow tan from true internal warming. Comets sometimes fire brief outbursts. Pieces of the crust crack and give a short jet. 3I Atlas hardly shows such salutes, and that's a clue as well. Either the crust is sturdy and pores are evenly distributed, or the warming proceeds from within so calmly that no surface shocks occur. Silence is a characteristic too. Sometimes viewers miss spectacle and are tempted to see signs of a technological system in a dry coma. In fiction, carbon dioxide often appears as a working gas for thermal regulation or attitude control. In reality, it's simpler. Frozen CO2 is a common inhabitant of a disk's cold outskirts, and if a body grew there, it's obliged to be present. A natural cause always goes first on the list. To tell one from the other, it helps to look at isotopes. Heavy hydrogen in water, D/H, and carbon-13 in CO2 tell us about the temperature and pressure in the material's childhood. We don't set up a lab beside 3I Atlas, but we do have mass spectrometry at a distance, long exposures and patient models. A couple of weeks of observations can sometimes replace tons of rock on the table. When studying the chemical portrait, it's important to remember time. The coma is a snapshot of here and now, while the nucleus is an archive of there and then. If the upper layer is heavily processed by radiation, it can mask depth. If cracks open older horizons, the voice of the past, on the contrary, sounds louder. Our conclusions change depending on how deep the Sun hooks into. There's a simple sign of depth, seasonality within a single passage. As 3I Atlas turns different hemispheres toward the light, activity can shift slightly, as if the comet changes weather. If the chemistry remains the same, the composition is uniform on the scale of the first meters. If it shifts, we're seeing patches of different origin. It's a map traced by the rotation itself. Another clue is dust speed. The easier the gas escapes, the more actively it carries off fine particles, and the tail becomes longer and thinner. A heavy, sticky mix behaves differently. The dust stays closer and the coma looks thicker. From the brightness profile along the tail, one can estimate what's pulling the dust, water or CO2. No guesswork needed here, just careful photometry. We're used to water being the main conductor of a comet because that's often the case with our domestic guests. 3I Atlas shows there are more scores to the symphony. In the galaxy's cold workshops, carbon dioxide can play first violin while water waits deeper in the nucleus. It's not an exception, it's another genre of the same music. Viewed without haste, the picture is simple. 3i Atlas grew where carbon dioxide froze readily and water not always. It lived a long time under the harsh light of cosmic rays and developed a dense crust. Now passing near our sun, it breathes as it's used to, quietly, evenly. More CO2, less water. Nothing mystical, just very beautiful. Should we expect water to speak up eventually? There's a chance after perihelion as the comet cools a bit and internal flows rearrange. Sometimes pore pressure changes and water breaks through locally, carving a short furrow in the tail. But if that doesn't happen, we still get a valuable answer. The pore network and crust truly hold water deeper down. Against this backdrop, repeats are especially important. The same spectral regions taken days and weeks apart show not only amplitude but the character of breathing. A smooth line is one story, a jagged one is another, with percussive episodes. It starts to resemble an ECG of a celestial body, where each spike is a small event in the depths. Work with the background brings a bonus. If we see how 3i Atlas is inscribed in the glow of interplanetary dust and reflected light, we better understand the boundaries of the coma itself. Then even weak gas bands become more secure, and we can talk in percentages rather than just seen, not seen. Precision is a form of calm too. Such details may seem boring. In truth, the most beautiful conclusions arise from them. 1 extra % of CO2 here, one slow step in brightness there, and the birthplace shrinks from somewhere far to this particular temperature band. That's the goal, to turn a stranger without an address into a letter with a postmark. If we listen closely, the chemistry will hint at the future as well. As 3i Atlas moves farther from the sun, its carbon dioxide breathing will weaken first, and water, if it didn't break out near perihelion, will remain silent. Then the curves will settle smoothly to zero, and we'll be able to say the archive is closed until the next star. That won't be sad, it will be honest. And yet every such quiet archive has room for a surprise. One crack, one tiny collapse is enough for a thin jet to flare for an hour or two. We're not obliged to see it, but we are obliged to be ready methodologically. Long exposures, consistent settings, clean observing logs. Surprises love discipline. The quiet conclusion is simple. 3i Atlas teaches us to accept dry comets as they are, without casting other roles onto them. There's no caps lock in its chemistry, but there is clarity. A childhood in cold, a coming of age under radiation, a maturity without lavish effects. Taken together, it's another version of how the universe gathers matter and sends it between the stars. Next, we'll look not only at what it breathes, but also where it might have come from at all, and how long it travelled. Chemistry has given us a direction. Now it's time for the geography of the galaxy and the timescale of 3i Atlas's journey. Calmly, without haste, at the same pace, from simple to complex. Chemistry has given us a direction, more carbon dioxide, less water. Now let's carefully try to answer two simple questions. Where might 3i Atlas have come from, and how many years was it on the road? We don't need heavy jargon for this. It's enough to remember that our galaxy is a vast city with its own districts, roads, and familiar traffic flows. The Milky Way is layered. In the centre is the bulge. Around it lies a pancake of stars and gas astronomers called the thin disk. Above and below is a thicker, more rarefied layer of old stars, the thick disk. Objects from this thick disk usually have more shaken speeds. Orbits are inclined, paths rougher, they don't lie so neatly in the plane. If we look at the path of 3i Atlas without sensationalism, we see just such a wanderer's behaviour. It arrived at an angle, is moving fast, and won't linger. A hyperbolic trajectory says something simple. The sun won't hold this guest. It flew in from interstellar space and will fly back out. Yet even from this single arc we can squeeze hints about the past. The direction of approach, the speed at infinity, the inclination, all these numbers add up to a neat clue. Most likely this is a visitor from the galaxy's older thick disk population, where stars and their leftovers have lived a long, quiet life and the traffic rules are stricter. Where do interstellar comets come from in the first place? In youth, any stellar system has lots of excess material: ice, dust, rocks. Migrating giant planets can eject some of these bodies outward, like a ricochet. Sometimes the kick comes from a passing star, sometimes from a teasing by several planets at once. In some cases, even a nearby supernova plays a role. It shakes the gravitational field enough for weakly bound bodies to be flung away forever. If 3I Atlas was born around a distant star, it had two paths into adulthood. The first, quick, a powerful gravitational boot and straight into interstellar darkness. The second, slow. Millions of years on the outskirts of its system, occasional close passes, gradual nudges, and only then, freedom. Both scenarios leave traces on the surface. In the first, the upper layers are less reworked. In the second, they spend longer under gentle but constant irradiation and micro-collisions. Cosmic rays are like the weather of interstellar space. They scorch the upper millimeters, change the colour, make the crust darker and denser. Over time, this hide starts holding heat differently, and the pores grow tortuous. We can't touch it with our fingers, but we see the consequences. Smooth, calm, breathing, without bright jets. When gas escapes more from within than explodes from the surface. People sometimes speak about the age of 3I Atlas itself, and here it's important not to overdo it. Numbers in the billions of years aren't a birth date down to the calendar, but a class estimate. It looks like material that formed very long ago in an environment of old stars. The coma's chemistry, the speed and the trajectory's inclination all point, in chorus, to just such a biography. We don't know the name of its home star, but we can narrow the district, as in a city, between these neighbourhoods, closer to the thick layer. Over long journeys through the galaxy, such bodies change not only their appearance. Every pass near massive structures, stars, gas, even dark matter clumps in dense knots, tweaks the course slightly. It's not a 90-degree turn, but soft strokes. Here a few tenths of a kilometre per second faster. There a degree more inclined. Over billions of years, enough strokes accumulate for the path of 3I Atlas to become a complicated line without sharp kinks. If we try to imagine its life, we get a peaceful picture. Somewhere on the edge of a distant system, it slowly grew from dust and snow, occasionally bumping into neighbours. Then one of the giants passed too close, and the light icy worldlet got a new open ticket. After that, many dark laps around the Milky Way's centre, rare encounters with gas clouds, rare flashes from distant explosions, and then our solar system on the next circuit. Why do we link old age with carbon-heavy chemistry? Because in the cold regions of protoplanetary disks, CO2 really can freeze where water already struggles. If a body lived in such conditions for a long time, that carbon dioxide character becomes fixed in the upper layers. Then interstellar weather compacts the crust and leaves channels through which CO2 in particular escapes more easily. On the far approach to our sun, that habit revealed itself. Stories about the galaxy sometimes use the phrase shift of standards. That's when the comets we're used to, Oort cloud visitors rich in water, seem like the norm, and everything else looks like a deviation. 3I Atlas simply shows that there's more than one norm. In another stellar kitchen, the recipe may be different. Less water at the top, more CO2, more patience and fewer fireworks. That's not exotic. It's another style of baking rock and ice. The speed of 3I Atlas, about 58 kilometers per second relative to the Sun, is also part of this biography. It's not turbo mode, but a typical speed for a body that inherits the motion of its native stellar population and adds gravitational nudges along the route. For us it's fast. Observing windows are narrow, angles change quickly. For the galaxy it's calm. That's how interstellar life flows. There's another quiet marker, the inclination. Our domestic comets often roam near the ecliptic plane, or at least cross it regularly. The Guest 3i Atlas moves differently, and that's normal for an object not tied to our system's history. Taken together, speed, inclination, and chemistry form a passport with no photo or address, but with a distinct character. Can we imagine that this isn't its first pass near suns like ours? Yes. Over billions of years, the probability of passing near planetary systems isn't zero. But those are distant encounters. A light bend in course, a couple of extra degrees of tilt, and on it goes. To hit the goal mouth exactly and become a long-term resident around a star would take an incredible coincidence, which we don't expect. People sometimes ask, could 3i Atlas have formed not around a star at all, but in a free-floating dark cloud? Such ideas sound appealing but are hard to support with simple evidence. As a rule, the observed chemistry and structure of such bodies are better explained by birth in a disk around a star, where temperature, pressure, and density gradients draw the familiar ice lines. We stick with the simple option as long as it works. If we sum up a provisional result, the picture looks like this. This is a guest from an old quarter of the Milky Way, born in the cold, travelling long through the dark, grown a dense crust, learned to breathe carbon dioxide, and not fond of loud effects. It doesn't have to fit our expectations. On the contrary, it widens them. With such meetings, any norm becomes broader and more interesting. Why do we need to know all this? Because behind chemistry and geography lies the main lesson. Interstellar wanderers are the galaxy's mail. They carry strokes from their home places, and by reading those strokes we learn what kinds of nurseries planets and comets have, what their habits are, and how often they fling their youngsters into open space. 3i Atlas is one such envelope, carefully delivered to our crossroads. The next calm question follows naturally. Why does an object with such a long biography and respectable size behave so quietly? What inside it keeps the process even, without bright fountains? To avoid guessing, we'll gently move from where and when to how it's built. There's no rush in this. The inner layers will tell their part of the story just as unhurriedly as the outer ones. It's large and surprisingly quiet. We're used to big nuclei behaving noisily, cracking, releasing jets, painting sharp brush strokes of tail across the sky. 3i Atlas seems to have chosen another way to speak, in a whisper. That doesn't make it less interesting. On the contrary, this polite manner makes us look closer and search for answers not in fireworks, but in details. Let's start with a simple question. Why, at roughly 11 kilometers across, does it almost never show bright jets? Ordinary comets have a familiar script. The sun warms the surface, ice releases gas, the gas sweeps up dust, thin plumes shoot off to the side, and we see jets. If there are no jets, something along the gas's path must be arranged differently. Imagine you set a kettle on a very low flame and cover it with a thick cloth. The water below begins to move, but you barely see any steam outside. It seems that, for 3i Atlas, the role of this cloth is played by a tough crust and very small winding pores in the upper layers. The crust isn't stone armour, but a layered bread crust formed over millions of years. Dust, charring and sintering makes the surface darker and denser. High-energy particles from space slowly overbake the upper millimetre after millimetre. Tiny fragments fall back like crumbs onto a table, and over time build a fluffy carpet. As a result, gas has to seek a long path outward rather than bursting out in a jet. It seeps like air through a dense sponge, evenly, without surges. Porosity matters too. If the top has many thin channels, like in pumice, carbon dioxide escapes more easily than water. Its molecules stick less to pore walls, and the temperature at which it boils off is lower. Under the same conditions, water tends to linger, refreeze, try again, and get stuck once more in the loops. The outcome is quiet ventilation. Outwardly, everything is calm, while inside, steady work goes on. Now imagine the nucleus rotates very slowly. Then the sun warms the same patch for a long time. Heat has time to penetrate deeper, but without sharp contrasts. When the warming is gentle, the surface doesn't take internal shocks. No blowing the lid off. If the nucleus is also slightly tilted, the hemispheres share the light more evenly by season. That again works against showy jets and in favour of steady breathing. Even if pressure builds up at depth, the way out doesn't have to become a fountain. The longer and twistier the pores, the more calmly the gas loses speed. Think of a path through dense woods. On a straight you run fast. In thickets you inevitably slow down. In 3i Atlas, the thickets of pores, bridges, micro-ribs, and sintered dust grains do their job. Gas exits evenly, dust is lifted, but without fine needles drawn across the sky. Dust isn't simple either. If grains are larger, they're heavy for such a gentle wind and don't travel far. The coma looks thicker and closer to the nucleus, the tail broader and blurrier without long strands. Fine dust, by contrast, would be carried away to make a thin brush stroke. Judging by appearances, 3i Atlas takes the first approach. Grains aren't too small. The wind lifts them but doesn't carry them off into a fine brush. The picture comes out soft without sharp lines. Sometimes flashes are noticed in images and it seems, here's the signal, something blinked. But optics can surprise. A cosmic ray strikes the detector. A bright star lands on the frame edge. Sunlight scatters in the lenses and we see false sparks. That isn't a trick by 3i Atlas, but noise along the path from the object to our eye. When such frames are reviewed, the flash often vanishes, along with mild disappointment and the instrument's preserved self-respect. There's another quiet reason for the lack of jets: slow glazing of the surface. Under heat, tiny particles can stick to each other, forming crustlets that seal off larger gas vents. Water and carbon dioxide look for detours, and again flow through a network of fine channels. Picture dry soil after a light rain. A thin crust on top keeps water from running down one or two cracks and makes it spread in a wide patch. Now about shape. At times, due to lighting angles and rotation, a body can appear flat or elongated. But at a distance, any outline is a play of light and shadow. To infer shape, astronomers watch how brightness changes over time. If the nucleus is like a potato, brightness rises and falls in a single rhythm. If there's a little wobble, i.e. complex rotation, the rhythm doubles and triples. For 3i Atlas, what's most noticeable so far are slow, calm variations, consistent with the idea that there's no acrobatics, no facet juggling. It turns in a measured way. How can we tell what's inside? We can't look in, but we have implications. If heat goes inward and returns slowly, the upper layers hold it like a wool blanket. That happens when there are many voids, narrow pores, and tight grain-to-grain contact. Then the thermal wave penetrates to depths of centimetres, perhaps tens of centimetres, and comes back not as a burst but as a gentle release. That's why comet tails often draw themselves most clearly after perihelion. Their internal kettle is still hot, though the flame is off. There's an opposite picture too. If pores are wide and open to the surface, gas rushes out briskly without time to cool. Then we see jets. That's great for spectacle, but not necessary for understanding. In quiet cases like 3i Atlas, data on internal structure are even cleaner. A uniform coma is like a voice without echo. It's easier to measure the timbre without being distracted by volume. Another quiet marker is how quickly the coma responds to changes in distance from the sun. If activity declines slowly, the sources lie not right at the surface. Gas manages to warm at depth and still reach the exterior. If the drop is sharp, gas is being born nearly at the comet's skin. For 3i Atlas, the curve looks closer to the first case, which fits gentle temperament and soft ventilation. By the way, a large body has another bonus, its own faint gravity. In absolute terms, it's tiny, but for dust grains, it's enough. Some of them rise a meter or two, then fall back, reblanketing the surface and making it even more carpeted. A self-sustaining cycle appears. Dust makes a blanket. The blanket makes jets rare. Rare jets fail to remove the blanket. In the end, everything runs quietly, but steadily. What season is it for 3i Atlas now? If we imagine it has putative poles, one receives more light before perihelion and the other after. If active spots are unevenly distributed, we'll see small brightness shifts with rotation. But so far the weather seems even. That again supports the idea of a uniform pore network and a sturdy upper crust without large open craters. Why do we keep hearing carbon dioxide rather than water? Because given this surface character, CO2 is precisely what can squeeze through more easily. It's born at depth, loses some energy in narrow channels, yet still makes it to daylight. Water is more capricious. It needs more heat or a more direct channel. If there are no channels, it stays quiet and we see carbon dioxide breathing. There's no mystery in this, just a different instrument setting. People sometimes ask, then why is a tail visible at all? Because even a gentle, steady breath produces plenty of gas and dust over months. It's like a slowly simmering soup. Watch not for a minute but for an hour and you'll still see steam above the pot. The coma and tail of 3i Atlas aren't spiky or noisy. They resemble a broad haze where the main thing is not a flash but the overall pattern. You might wonder, is it really true that flashes in frames are usually not signals? Yes, and it's a useful reminder. Cameras in space and on Earth aren't perfect. Particle trails, interference, stray reflections, even a thin frost on a lens can get in the way. That's why patient astronomy uses so many repeats. 1 frame is romance, 10 frames are material, 100 frames are character. 3i Atlas isn't in a hurry, and neither should we be. Let's talk mechanics. If the crust does crack suddenly, we'll see a brief salute, a narrow jet for an hour or a day. But a strong surface with fine cracking may not allow major blowouts at all. Any attempt to build up gas in a pocket ends with it seeping into tiny fissures and the pressure dropping quickly. So big explosions don't accumulate, they die in the cradle. This isn't stealth, it's simply good ventilation. It's also interesting how heat is distributed. In a fluffy material it travels slowly. There's the notion of a skin depth, the layer to which daytime warmth reaches. If it's shallow, day-night changes are sharp and obvious. If deeper, diurnal swings smooth out, but seasonal ones grow more important. For 3i Atlas, the season now is singular. It's moving away from the sun, and the internal stored heat wave is just beginning to give itself back. That's why comets sometimes look more active after perihelion. Heat returns slowly. We talk a lot about quiet, but quiet isn't absence. It's a different genre. In the quiet regime we can make measurements impossible amid smoke and sparks. We can split the coma's light into fine lines, watch carefully as they rise and fall day after day, and by these smooth, almost musical curves judge the depth and structure of the upper centimetres. It's a kind of acoustic tomography, only with light instead of sound and the coma instead of a body. Why does all this matter? Because internal structure tells us not only about 3i Atlas, but also about the environment where it was born. If the upper layers are so pacified, its childhood likely lacked upheavals and frequent recasting. It didn't get repeatedly scorched by close swings around its home star. It lived farther out, where gradients are gentler and rhythm calmer. That's already indirect evidence of a distant cold origin. Another subtle detail is dust fallback. In weak gravity, particles don't behave as on Earth. They clump, charge, and stick to the crust. The result is a surface that gradually becomes smoother on the meter scale and rougher on the millimeter scale. Such micro-relief also works against large jets. It divides the gas flow into many small paths, like a network of irrigation channels in an old field. It may seem that in this quiet it's easy to miss something important, so observations are designed to see with several eyes at once. Normal cameras show the coma's shape. Infrared instruments spot warm patches where gas emerges more actively. Radio observations help estimate grain sizes. Polarization filters tell how light scatters and how smooth the particles appear. Put it all together, and the picture stops being a guessing game. There's a cultural side too. We love stories where the cosmos gives a sign. We expect a miracle in the form of a flash, a beam, a sharp shadow. But a miracle can be this as well. A great interstellar traveller passes nearby and shows a different normal, the normal of quiet breathing, where all meaning lies in the smooth lines of graphs. We shouldn't consider that normal poor. It's simply mature. Should we expect Three-Eye Atlas's character to change abruptly? In theory, if the crust weakens significantly somewhere, or a fresh layer richer in water opens up. But everything we see so far argues for stability. Evenness is its style. And that's a fine gift to those who love long observing series. Stable systems are easier to study than capricious ones. Sometimes the direct question comes, what's inside? A monolith or a rubble pile? At this distance, it's almost impossible to say for sure. But the behaviour points to a fluffy nature with many voids and channels. A monolith would produce sharper effects when cracking, whereas a rubble pile damps them like a soft cushion. So again, the bet is on quiet, on distribution, on porous logic. If we try to assemble the whole story into one picture, it looks like this. Three-Eye Atlas has a tough but not rock-solid crust, a network of fine pores through which carbon dioxide passes more readily, slow rotation and even illumination, somewhat coarse dust that lifts but doesn't fly far, faint self-gravity that returns some, crumbs back, and a thermal skin depth sufficient to keep the kettle warm for a long time. Together that yields a large yet secretive character, a calm, steady breathing without fireworks. What should we do with this knowledge? Keep watching and listening. If an opening does appear somewhere, we'll notice it. If not, we'll assemble a complete portrait of quiet that will be useful for the next interstellar guest. And perhaps, thanks to Three-Eye Atlas, we'll understand in advance that not every big comet is obliged to put on a show. Sometimes the most valuable skill is reading the whisper without demanding a shout, and the next simple step suggests itself. If we want to stop guessing from afar, we do well to see it a bit closer, at least through the eyes of a passing spacecraft. Swing a camera quickly, shoot a series, snatch the fine structure of the coma from the darkness, and lay it out neatly. Ground-based telescopes will do their part, but a view from a vehicle is like taking one step closer to a painting. Not for sensation, not for loud headlines, but to calmly add the missing strokes and understand how exactly this large, wonderfully quiet Three-Eye Atlas is built. We've already learned to listen to the quiet of Three-Eye Atlas and to find meaning in it. The next natural step is to get closer, not for effect or dramatic footage, but to answer simple questions with simple measurements. What the surface is made of, how the upper layers are arranged, what happens to the dust, where the gas is born and how it escapes. In engineering terms, this sounds simpler. We need a few sensors on the right trajectory at the right time. Behind that simplicity lies one of the toughest tasks for modern spacecraft, to catch an interstellar guest that flies faster than we're used to and does it only once. Let's start without romance, with constraints. 3. Atlas follows a hyperbola, fast, at an unusual angle to the plane of our planets, and most importantly just once. That means there's little time to prepare, and the windows for favourable trajectories are narrow. The second issue is relative encounter speed. Even if a spacecraft catches the target, the closing speed near the rendezvous may remain so high that detailed imagery turns into a difficult attraction lasting fractions of a minute, hence a basic trade-off. The faster we launch and chase, the less time we have near the object. The longer we save propellant and execute maneuvers, the more likely we are to be late. It helps to separate goals right away. First, remote ones. Good optics, spectra in the visible and infrared, polarimetry for dust, brightness measurements over time. These can be collected from the ground, from orbit, and possibly during a flyby by another spacecraft. Second, in situ ones. On-site analysis of gas and dust, close-up images of coma structure, estimates of particle density nearby, surface thermometry, searches for local breathing spots. For that we need our own Scout, small but fast with solid. Shielding and communications. Against this background there are several architectural options. The most direct is a small, fast spacecraft with a powerful kick stage and a series of gravity assists. The classic staircase looks like this. Launch with the maximum available energy, then one or two hops around Earth or Venus to change inclination for free and stretch the orbit, and finally a sharp burn at solar periapsis using the Oberth effect. The idea is simple. The closer to the Sun we fire, the more value each kilogram of propellant yields, because the speed there is already high. The difficulty is that it's hot near the Sun, so we need a thermal shield and tight thermal control, like solar probes that have already taught us not to fear close passes but to plan them correctly. The second path is electric propulsion, ion engines that work long and quietly. They can't deliver big jolts, but they can add millimeters per second week after week, month after month, adding up to a large gain. Electric propulsion needs power though. Close to the Sun, large solar arrays work great, but farther out their effectiveness drops, and most of the science at 3i Atlas is useful at some remove from the bright disk. That means either accepting reduced thrust or thinking about alternative sources, compact generators that provide steady power regardless of distance. The third point is time. Ion patience is good for next-guess missions where we can launch early and wait in ambush, but it may be too slow for an event already underway. There are bolder ideas. A solar sail can accelerate a craft without propellant by riding light pressure. For intercepting a fast interstellar object, a traditional sail will likely be too slow. It needs a very long time to build speed and is sensitive to payload mass. But a sail is interesting as a readiness element. Lightweight deployable platforms could be kept on standby in solar orbit, and upon news of a new target simply reoriented to head it off. That thought isn't about 3i Atlas, but about the next object. This is how long plans are built, not for a specific guest, but for a class of events. Between these extremes lies the idea of a solar thermal sprint, using the Sun's heat as a boiler to warm a propellant and expel it at high speed. It's the Oberth effect in another wrapper. In theory, such a burn is very efficient, but it requires radiators, heat-resistant materials, and precise navigation to avoid overheating the craft. The beauty is that this maneuver can be combined with gravity assists. Climb, dive toward the light, make a sharp step outward, and then tune the phase to 3i Atlas. Whatever propulsion we choose, navigation is its own story. Approaching an object that shows few bright jets and behaves steadily, we lose high-contrast beacons. Optical navigation will rely on subtle changes in the coma's shape and the motion of dust contours. At the same time, camera fields will be cluttered by stars, glints, and flares. Algorithms will need to tell useful lines from noisy ones, and do it autonomously, without long command loops from Earth. The encounter itself will most likely occur at high relative speed, so the observation plan resembles choreography. Pre-scripted camera slews, exposure sequences, and measurement intervals for each instrument. Now about shielding. Even a quiet coma contains lots of fine dust at high relative speed. We need micrometeoroid shielding, multi-layer bumpers that fragment a grain before it can pierce the structure, it's best to place the most vulnerable elements, tanks, electronics, in the shield's shadow and use inflatable or deployable barriers for the short close-pass interval. For optics, a simple rule fits: short observing windows, peek, hide, peek again, to reduce the risk of particle hits at critical moments. We can keep the payload modest but precise: a high dynamic range camera for coma and tail structure, a compact infrared spectrometer for water and carbon dioxide lines, able to work fast with short exposures, a dust detector that counts particle impacts and infers mass from impulse, so we learn what dust is wandering nearby, a miniature mass spectrometer for local molecules, not a lab on wheels, but at least a basic periodic table for the gas, a polarimeter to learn how light scatters and what that says about grain shape and size. Finally, a simple radiometer to estimate surface temperatures if we can peer through windows in the dust. Communications are another compromise. Near the object, we want to shoot fast and a lot, but the link to Earth isn't elastic. The solution is simple: onboard buffering, batch downlinks, lossless compression where possible, controlled lossy where it won't harm the science. Plus preset priorities. If the link sags, the spacecraft first sends miniature survey frames and short instrument reports so the ground can request repeats of the best moments. This mode has saved high-speed flyby missions more than once. Can we do without our own scout and get it all piggyback, say, catching 3i Atlas in the field of view of a spacecraft en route to some other destination? Sometimes that happens. Geometry allows it, schedules align, a camera is free, but we can't rely only on such luck. It's much more honest to have a simple playbook for interstellar visits, a set of standard instruments, a compact platform, a roster of kickstage providers, and pre-computed trajectories to taste for different approach angles. That playbook can run as a conveyor. Step 1, discovery and rough parameter estimates. Step 2, automatic checks against ready trajectories and a realistic versus pretty filter. Step 3, fast choice of a couple of instruments for the job and reserving a slot on the nearest launch with a suitable kickstage. Step 4, tailoring thermal protection and navigation algorithms depending on how close we must dive toward the sun for the Oberth effect. Step 5, tight but short ground testing, without trying to invent everything anew in a month. In this scheme, what matters isn't platform perfection, but readiness today. Of course, the bottleneck isn't only physics but organization. The simpler the payload, the higher the chance to make it in time. One instrument, one camera, one primary goal. This is sometimes wiser than 10 instruments and a long wish list. Such modesty also saves energy and mass, giving freedom in trajectory choice. An extra sensor is an extra kilogram of shield, an extra watt to heat in winter, an extra gigabit we won't transmit anyway. In a chase for an interstellar guest, the winner isn't the one with more, but the one with clearer focus. Navigation won't end at the object. After the flyby, the craft will fall onto a new orbit, often inconvenient for communications and of little use for further science. Even then, it retains a role as an experience relay telemetry, algorithm logs, shield behavior in a dust shower, panel degradation after a solar bath. All of this becomes a blueprint for the next attempt. We rarely build a perfect mission on the first try. It's better to build a well-prepared repeat. Now to risk management. The main threat is being late. The second is overheating on the solar dive. The third is losing attitude due to sensor blinding during approach, when the field contains the coma, the sun, and bright stars. The fourth is dust, a random hit by a large grain at the wrong moment. Remedies: pre-baked scenarios with hard limits, multiple independent navigation cues, a software shutter against overly bright frames, physically separating critical subsystems behind the shield, and not fearing to pause observations if the environment suddenly turns hazardous. Is a swarm approach, several microscouts instead of one craft, worth considering? Yes, it's a natural idea. 10 tiny sensors raise the chances that at least some get through the dust and return data. They can divide roles, one for dust, another for gas, a third for close imagery. The downside is comms and coordination. Each needs its slice of the downlink, so priorities must be set firmly and some losses accepted. But as part of a playbook for future guests, it's a sensible line. A separate question is ethics and protocols should we see signs of the non-natural. The rule is simple. Without solid evidence, active actions are off the table. No pings, no spotlights, no attempts to nudge the object and listen for a response. Only passive measurements and careful analysis. All the science fiction stays in the next room. We stick to the work schedule. It's not timidity, it's grown-up discipline. First be sure you're seeing what you think you're seeing. Everything said may sound like a list of difficulties, but in truth it's a list of opportunities. There's nothing supernatural here. We know how to build thermal shields, we have electric propulsion, we understand gravity assists, and we can script autonomous camera choreography. The newest element in a mission to 3i Atlas isn't hardware but time management. What usually stretches over years must be packed into months. Unusual, yes, but that's precisely why readiness pipelines exist. Looking back at the goal, it remains surprisingly down to earth. We need close-ups of coma and tail, a basic gas composition, dust size statistics, spot temperature estimates including contrast patches, a few brightness curves on the way out of perihelion, and a short series beyond peak activity. Everything else is a beautiful superstructure. If we must choose, better to get confident simple results than uncertain complex ones. It's worth mentioning an alternative to the dash option, a calm but longer project, keeping a permanent on-call platform in solar orbit. It doesn't chase anyone. It waits where interceptions are statistically favourable. Spot an interstellar object whose parameters fall in the corridor, wake the platform, tweak the phase, close in. Such a system costs more at launch but less in nerves. In exchange, we get not a race for one, but readiness for many. Alongside engineering, we shouldn't forget what already works. Ground telescopes that can watch faint lines patiently for long stretches, networks that can catch the radio whisper of dust, processing methods that tell a sensor flare from a spark in the coma. If we manage to catch 3i Atlas in the field of view of a spacecraft already in flight, great. If not, these tools will still weave the fabric of facts on which any future mission will rest. Take in the whole picture, and a simple thought arrives. Interstellar guests aren't anomalies, they're part of solar system life. We'll meet them suddenly and almost always only once. The best strategy, then, is not to wait for the perfect case, but to form the perfect habit. Keep a tidy plan at hand, don't bloat the payload, admit constraints honestly, and quietly take what's realistically available. 3i Atlas doesn't mind modesty, it doesn't care how exactly we look at it. What matters is that our gaze is confident. And finally, the human part. Missions like these aren't built from a desire to catch up at any cost. They're built from respect for simple knowledge. A close look answers where a distant one sparked debate. A handful of images, a couple of spectra, and a scatter of dust detector hits often close dozens of pages of theory. We don't promise miracles, but we do promise discipline. That's enough to ensure the next dot on the map of interstellar wanderers is not only beautiful, but also clear. Even if we don't reach 3i Atlas with a perfect plan, the mental path we've just walked already makes us readier. Next time the list will be shorter, the doubts fewer, and the launch closer. That is the quiet benefit of meeting a large but modest guest. It makes us tidy our thoughts, tools, and time, which means that when someone from interstellar depths appears again at our celestial crossroads, we'll not only be glad to see them, we'll be ready to sit down, open our notebook, and calmly write down what matters most. Sometimes the most interesting stories are told by those who speak the quietest. Three-Eye Atlas is exactly such a guest. It makes no abrupt gestures, shows no bright jets, and puts on no light show. Instead, it patiently lets us listen to what noise usually drowns out. The longer we watch, the more we understand. There is logic in this quiet, and it leads us further, to questions about nature, about ethics, and about which quiet signs are worth taking as hints of artificiality at all. First, why humanity so readily tries on fantastical scenarios for interstellar objects. We grew up on stories of sails, probes, and signals, and any unusual comet instantly falls into a ready-made grid of explanations. That's normal for human imagination, but science brackets things differently. Before we embellish, we subtract the excess. With Three-Eye Atlas, there isn't much excess. A hyperbolic trajectory, a dry coma, steady behaviour, and rare hints of flashes that are more often explained by optics. None of this calls for sensation. All of it calls for discipline. What signs could count as quiet markers of artificiality? First, unusual geometries that persist over time and can't be explained by lighting angles. In other words, a stable flat shape that behaves like a thin sail under light pressure rather than a cometary potato. Three-Eye Atlas shows no such stable geometric. Signatures. Brightness variations are calm without the characteristic sail pulsation, and irregularities fit easily into familiar cometary botany. Second, puzzling non-gravitational thrust not tied to natural outgassing. This came up years ago with another interstellar visitor, so we treat it warily. For Three-Eye Atlas, there's no indication that someone has a foot on the gas. If there are microscopic deviations from pure gravity, they should be explained by that same steady CO2 breathing we observe, and that fits neatly into the spectrum. Third, chemical anomalies at the level of isotopes and trace elements, places where the kitchen of natural processes follows known recipes. If we saw combinations that don't assemble well out of ordinary cosmochemistry, that would be a substantive reason for new checks. But so far, the chemistry of Three-Eye Atlas says something else. A childhood in a cold region, a long spell of radiation weather, and a porous upper crust that releases CO2 more readily than water. And finally, a fourth marker. Signals, rhythms, modulations that are hard to attribute to rotation, precession, or instrumental effects. Here we're especially strict with ourselves. We repeat observations with different instruments, change filters, move cameras, so as not to confuse the whisper of the sky with the noise of equipment. Three-Eye Atlas has shown no rhythms resembling a transmission so far. What it does present is the unhurried music of cooling and sublimation. Ethics in this story doesn't sound like a limitation, but as a way not to spoil what's most valuable, the ability to understand. We don't ping the object without good cause, we don't spotlight it without methodological agreement, and we don't provoke processes that could alter the surface. Our task is simple and hard at once, to be nearby as observers, not participants. There's no coldness in that. There's respect for information, and for those who will work with it next. People sometimes ask, why not try active diagnostics? Say, pulsed laser illumination to assess reflectance? The answer lies in balance. Any active method must add enough knowledge to outweigh risks and noise, and it mustn't stretch interpretations. As long as Three-Eye Atlas is open to passive measurements already, the best strategy is the familiar set: spectra, photometry, polarimetry, radio observations. Taken together, they yield more than it seems. If we imagine a hypothetical technogenic scenario, it doesn't have to shout either. A technological object on a distant flyby could look very restrained. A smooth panel, a radiator, a thin screen. Against such a backdrop, it's easy to confuse neat engineering with a flat facet of a natural body lit by a particular angle. That's why we insist on repeatability. A single frame can deceive, a series hardly. There's a useful, simple principle. Try to explain the unusual with the usual, but not by fitting the curve. If you need 10 assumptions to make the natural picture work, the picture is probably bad. If 2 or 3 simple assumptions tuck neatly into the observations, we're on the right track. With 3i Atlas, it's the latter. A cold childhood, an over-dried crust, slow rotation, somewhat coarse dust, and carbon dioxide breathing. Not a monster scenario, an honest skeleton of explanation. Why does this matter for the future? Because 3i Atlas helps assemble an alphabet of interstellar guests. Today, a letter, tomorrow, another. In a few years we may have an abecedary by which we'll read such wanderers without panic and without haste. For that to happen, each object needs the right to be itself. 3i Atlas behaves exactly this way, calmly, without trying to become someone's proof exhibit. Practically, we carry out of this quiet story a concrete checklist of signs worth watching for next time. First, shape and its stability over time. Second, the subtle dynamics of the coma, how light polarizes, how brightness changes, and where exactly spots appear. Third, isotopic compositions if we can extract them with good precision. Fourth, any stable non-local rhythms that don't vanish when we change instruments and viewing angle. Of course, beyond possible artificiality, dozens of natural questions remain that 3i Atlas helps us pose. How diverse are Comet's nurseries beyond our system, for instance? How long does the radiation crust persist, and how quickly does it self-repair via dust rain? What might the carbon landscape look like in different quarters of the galaxy if a single flyby so clearly shows the arrangement of ices? A separate topic is the slow science of data. We're used to frames that talk right away, but the real work often begins months and years later. Long spectral series, seasonal comparisons, careful corrections for weather, dust and instrumentation. None of this looks like a show, but that's where confidence hides. 3i Atlas is an ideal object for this work. It isn't capricious, holds a steady line, and lets us accumulate quiet centimeters of knowledge. There's a temptation to look for a single decisive sign that proves everything. But the world works otherwise. It's more often assembled from small straight lines than from one bold stroke. That's why we keep returning to repeatability, to simple curves, to not yanking on a single event. If something new appears in the behavior of 3i Atlas, we'll notice it, because we already know its calibration. If it doesn't, that too is a result and no worse. We've talked a lot about what if it's a ship, but there's an equally important flip side. What if it's simply a comet of a different genre? There's nothing reductive in that simply. Another genre means a new class of conditions, new constants, different proportions of CO2 and H2O, different porosities and thermal conductivities. In technical language, our models need widening. In human language, we've met a new character who also lives in our cosmic city. Practically speaking, 3i Atlas reminds us we need readiness without hysteria. That applies not only to hardware playbooks, but to society at large. Headlines about ships are beautiful, but their real price is lost attention to quiet work. Better to repeat the boring, measured, checked, confirmed 100 times than to make one loud mistake. This isn't a posture, it's a way to save what's most precious, time and trust. Perhaps the main human lesson here is knowing how to live with uncertainty properly. Not to push it away, not to fill gaps with fantasy, but to accept and work. With 3i Atlas we truly don't know a lot, but we know how a lot becomes less, through patience, repetition, and respect for simple data. Sometimes that is maturity, to let the world remain complicated and not force it to accelerate to fit a storyline. If, someday, we do come across a real technogenic trace, it's precisely such calm stories that will have prepared us best. By then we'll know how to tell optics from signal, we'll be used to slow curves, and we'll stop pulling the blanket of interpretations over ourselves. Then a small sign won't be lost in noise, and a big one won't be taken as a sensation where there is none. Three-Eye Atlas is perhaps not about a ship, but it is certainly about a compass. There's also a small but important poetry in this story. Interstellar wanderers are like letters with no return address but with a recognizable hand. Three-Eye Atlas is written evenly, in a calm adult hand. There are no flourishes or exclamation marks, but there are many neat lines. They're about how CO2 freezes in the cold, how channels live in a porous crust, and how quiet can be more informative than fireworks. You want to fold this letter carefully and file it under Learn to Listen Now, the promised wrap-up. We close our calm cycle about Three-Eye Atlas without slamming doors, but by closing them softly and securely. We've talked about trajectory and speed, about chemistry and heat transfer, about the large but quiet nature of the nucleus, about a possible interceptor mission, and about how to tell fiction from physics. What remains is a short, honest conclusion to call things by their names. Summary. 3. I Atlas is an interstellar guest with a hyperbolic trajectory, a large nucleus, and a dry coma in which carbon dioxide stands out more than water. Its behaviour is steady. There are almost no bright jets, and flashes in images are more often optics than the object's physics. All this fits best into a picture of a cold birthplace. Prolonged radiation weather, a porous crust, slow rotation, and somewhat coarse dust that doesn't hurry to form a thin tail. An interception remains a technically tough task, but even without a close visit, the totality of passive observations yields a confident, coherent portrait. Conclusions. We have no reliable grounds to regard Three-Eye Atlas as an artificial object. We have good natural explanations for all observed features, and they are mutually consistent. This story is more about discipline than sensation, more about patience than headlines. Its main legacy is readiness, to tell the whisper of data from the noise of expectations, and to carry a practical toolkit for the next interstellar guest. I think that Three-Eye Atlas is an honest, natural comet of another genre, whose dry chemistry and quiet behaviour are best explained by a cold childhood and a porous upper crust. I think that the search for quiet markers of artificiality should begin with impeccable tests of natural models, and only then move on to bolder hypotheses. I think that our chief tool here is not a loud experiment, but long series of simple observations, spectra, photometry, polarimetry, radio data, taken patiently and repeatably. I think that even if we don't make a close intercept, the mere preparation of playbooks and methods is already an important step toward the day when the next interstellar guest appears at the crossroads of our orbits. I think that the main wonder in this story lies not in mysteries, but in the ability to hear the quiet. We really are learning to look more calmly, and seeing farther because of it. We end not with a period, but with a comma. Three-Eye Atlas goes farther on, but leaves us with a very clear feeling. The solar system is an open space where familiar stories live alongside new genres. If we keep a calm gaze and honest methods, every next encounter will be not a trial by sensationalism, but an exercise in understanding. That is what mature astronomy is, listening to the cosmos so that it trusts us with its whispers.